Yeah.
So funny.
Okay, so we're on 2.3, the electromagnetic spectrum.
What does NM stand for?
Nanometers.
Never mind.
Do you know the all the metric prefixes? And can you say them in less than 5 seconds? Gigamega, kilo, hectodecadec, centimilli, micro, nano, pico,
What about the Greek alphabet?
I'm going to give it a little say anything, I'm going to use some make it. Okay, so enough of that. Enough about how great I am. So, have you ever seen a rainbow before?
I saw a double rainbow last
night.
I saw a rainbow yesterday.
Last night on the beach.
Double rainbow.
Yeah.
All the way across the sky.
Why does it have all these different colors? Well, it depends upon, color depends upon the wavelength of the light. And light comes in a bunch of different wavelengths or frequencies. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So our eyes can detect light that goes from 400 to 700 nanometers wavelength. That means the waves, and remember, light is in waves now, comes in wave form. That's very good drawing of waves. So the distance between one crest and another is the wavelength. If that wavelength of light is between 700 nanometers and 400 nanometers, our eyes can detect it. So if anything that has an electromagnetic wave between 700 and 400 nanometers, we'll see as visible light. And a nanometer is small. A nanometer is a billionth of a meter. So these waves are really small. They're not like big ocean waves. They're really tiny waves that our eyes detect.
Oh boy.
So if it's closest to 700 nanometers wavelength, those are long wavelength light. I mean, they're not actually long, but they're the longest ones our eyes can see. That's red. And if it's short wavelength light, 400 nanometers, that's violet. If the wavelength is even shorter than 400 nanometers, we call it ultraviolet. Above violet. And if it's longer than 700 nanometers, we call it infrared, below red. You see where they get that? Ultraviolet and infrared? I've had several students, and don't feel bad if you thought it too, when they hear ultraviolet, they thought it's ultraviolent, like violence, because they're ultraviolet waves, because that gives you sunburn. It's not ultraviolet, it's ultraviolet. You see? So as we go this way in the spectrum, the wavelengths get shorter and shorter. And as we go this way in the spectrum, the wavelengths get longer and longer. As a general rule of thumb, the shorter the wavelengths are, the more energetic they are. So as you go this way, you get more and more energy. It takes more and more energy to produce short wave radiation than long wave radiation. Because the object that produces them, remember, to produce radiation, you have to have a vibrating object, right? And if the object is vibrating really fast, then the wavelengths are short. It's like taking the end of a rope and doing it really fast, the rope's going to have these shorter waves, right? If you take the end of the rope and do it like this, you'll get longer waves. If I had a jump rope, we could do it, but I don't have a jump rope. I'm really good at jump rope, by the way. I'm like those, those boxers that do this. Once again, I'm good at a lot of things that y'all aren't.
Fishing?
Fishing? Pretty good.
Yeah,
That's a good question. What's that?
Ping pong.
Very good.
Underwater basket weaving.
What's that?
I'm better.
You're better at ping pong? We'll have to play. You probably are better because you play so much tennis. But we also have to play tennis too. We've got that battle. So I think I know you'll beat me, but it'll be fun to try. Okay. Anyway, enough about me. So radio waves are the lowest energy waves. They're real long waves. Gamma rays are the highest energy waves. They're real short waves. You got to memorize this whole electromagnetic spectrum if you haven't done that already. How many have already memorized the electromagnetic spectrum at some point in their school life?
We're supposed to do that in physical science. But I didn't memorize it.
The shortest ones are the shortest wavelength. Wavelength and frequency are, the shorter the wavelength, the higher the frequency. So these have an inverse relationship. As the wavelength goes down, the frequency goes up. And as the wavelength goes up, the frequency goes down. So radio waves come in at a lot lower frequency than ultraviolet or X-ray or gamma ray. So these are not different things. Everything on the spectrum is an electromagnetic wave. It's just that if the waves are coming in real fast, you call them gamma rays, many waves per second. If you're not getting very many waves per second, you call them radio waves. If you're getting somewhere in between, you can actually see them. Your eyes can actually pick up a little bit of the entire spectrum if it's coming in at the right wavelength. And if you just change that wavelength a little bit, you can't see it anymore.
Why does it say screen pointing to the infrared box?
This is a screen. If you take a flashlight and you shine the light through a prism, and then let the light hit a screen. That's what the screen is. It'll be broken up. There'll be colors that you can see, and then over here we'll be hitting infrared and radio waves, and over here would be hitting ultraviolet, X-rays, and gamma rays. If there were any gamma rays coming out of a flashlight. There's not any gamma rays that come out of a flashlight. It's not hot enough to produce them. The hottest thing that comes out of a flashlight is some ultraviolet. No X-rays come out and no gamma rays. But if you got that filament hot enough, you would produce X-rays and gamma rays. Question?
Oh, yeah. Does it produce radio waves?
It will produce radio waves, yeah. Radio waves are produced, it basically goes like this. The colder the object, the less energy waves are produced. So anything that's producing visible light is also producing infrared and radio. If it gets cooler, it won't produce any visible light, but you might produce some heat. Some infrared is heat. Heat and radio. If it's even colder than that, it won't even produce infrared, it'll just produce radio. Anything that has any temperature at least will produce some radio waves. Even if it's 1 degree Kelvin, it'll be producing a little bit of radio waves. Because it's got electrons, it's got particles that are moving. The only time you would produce no electromagnetic radiation is if all the particles are completely stopped. That's absolute zero.
I have a question. Come here. I want to know why the light does that.
Here now.
That's a good question.
It's rainbow.
The thing picks up
The like all
the wavelength of the light, but it's kind of like a strobe effect. It only picks up a certain number of frames per second, and that the rate that's picking it up is different than the rate that light is sending it out, and it has that effect.
What about when you're polarized
know that
across
by
the
now.
line and you look at like a screen?
Yeah.
Well, I didn't.
Yeah, that's the same thing. The sunglasses are acting like the prism here and breaking up the light. See, white light actually has every color of the rainbow in it.
Fine.
And white light is a kind of an equal mixture of red, orange, yellow, green, blue, and violet all together. That produces white. So white is actually all colors at once. And what's a total lack of any color? That's black. Olivia's finally here.
Well, look who decided.
Where were you? Oh, yeah?
Likely story.
Did the doctor say anything to you about a possible quiz?
Before you go
Okay, so let's look again. This is a great picture, and you should become intensely familiar with page 49. This shows the entire spectrum. Now notice this is a logarithmic scale. A logarithmic scale is a way to show great variations in a small amount of space. Notice every step up on the scale in frequency is a 10 times step up. So 10 times greater, 10 times greater, 10 times greater. And notice this about the spectrum. Visible light is just this little small area of this entire spectrum. Visible light is we can only see a little bit of the spectrum. Look how much radio waves take up. AM radio is at lower frequency than FM radio. AM radio is in kilohertz frequency. That's thousands of waves per second. Whereas FM is in megahertz. That's millions of waves per second. A microwave oven uses radiation at about 100 gigahertz. That's 100 billion waves per second. And that's the exact frequency. If you send radiation through your microwave at that frequency, it vibrates water molecules. Water molecules will vibrate if they're hit by radiation at 100 gigahertz. And so that's why your food heats up, because the radiation is vibrating the water molecules. If you put something in a microwave that doesn't have any water in it, it won't heat up.
Like dry macaroni.
Like dry macaroni. You got to put water in there.
Well, will it get any hotter?
If it has no water molecules, it won't get any hotter. If you just put a piece of paper in there, there's no water molecules in the paper.
Is it true that like if you put like a fake broccoli in like a microwave, it makes it look like less healthy?
I don't know.
That actually is true.
I don't know why it would
It
make
might
it
make sense.
It's true. If
The
you
next one,
boil it in water.
Breaks down the cellulose probably, and after the cellulose breaks down, you don't have the roughage in there to clean
You
your
drink
system
the water
out.
that you cook it in.
Well, can't microwaves, like if you eat enough food out of the microwave, can it like give you cancer? Or am I
No,
just totally wrong.
totally wrong.
Okay.
That's a wives' tale. That's a sexist thing to say. So microwaves are actually part of the radio wave spectrum. So everything below about right here, frequency of 10 to the 11th, is considered radio waves, including microwaves and FM radio and AM radio and what they call shortwave radio. Can you guess what shortwave radio? Have you ever heard of that, shortwave radio?
No.
There's a few old guys around that have these huge towers in their backyards, and they have a shortwave radio, and they can tune in like Japan and stuff, talk to people from around the world. It's kind of a dying hobby. But shortwave radio operates. I think it's in between these two. It's either in between these two or over here. Anyway, kind of an interesting. But there's a lot of stuff in the radio spectrum. The radio spectrum goes on to the very lowest frequencies where the molecules are barely moving at the coldest temperatures. Everything produces some radio waves because everything has a temperature greater than absolute zero. Infrared is known as heat. Those are heat waves. And you can't see them, but you can feel the heat. If somebody hands you, if somebody hands you a hot object, you might not be able to see that it's hot, but you could touch it and, oh, that's hot, And so that's infrared waves. Infrared waves produce heat. Now if you keep applying energy to the object, let's say you take a piece of iron and you put it in the coals for a while, and the coals keep giving it energy. And guess what happens when you pull that iron back out after about an hour? What's it look like? It's glowing. See, it's hot enough where it's not only producing radio waves and heat, it's also producing light. And if you watch something that starts glowing, it always starts red. And the hotter it gets, it'll go through the spectrum. And the hottest things are blue. But actually what it'll do is it'll eventually turn white hot. When it has all of these colors in it, it'll look white. Something that's white hot is a lot hotter than something that's red hot. And then finally, if the object gets hot enough, it'll start releasing ultraviolet. And ultraviolet comes in near, that means it's near to the visible, or far ultraviolet, that's far from the visible. Far ultraviolet is far more damaging than near ultraviolet. But these are the rays. Ultraviolet is what gives you a sunburn. You can't see it, but it will penetrate your cells and damage them. It'll damage the DNA of the cells and cause mutations and such, and that's what leads to skin cancer. Ultraviolet radiation. The sun is so hot it produces a lot of ultraviolet radiation that comes down through our atmosphere and hits our skin. Most of the ultraviolet radiation that the sun releases is blocked by our atmosphere. The air in the Earth's atmosphere blocks most of the ultraviolet radiation. There's a particular layer, do you know what it's called?
Ozone.
The ozone layer that blocks a lot of it. You ever heard of the ozone layer? We had a problem in the last 100 years. We were producing a chemical that destroyed the ozone layer. What do you think would happen if the ozone layer were gone?
You can't go outside anymore.
Why not?
Because you're going to get sunburned.
You get sunburned really fast. People nowadays get sunburned a lot faster than people did before we made those chemicals that tore up the ozone layer. And they've made a law to get rid of the chemicals. Does anyone besides Wayland know the names of the chemicals that tear up the ozone layer?
I know what they were used as.
That's
HCGs for pregnancy.
It was just the pesticide.
Yeah?
And
Is it
No, not pesticides, sorry.
Why am I being excluded from this?
refrigerant.
It was used in air conditioners and as a refrigerant. What's that?
The aerosol can.
Yeah, it was used in aerosol cans.
Why am I excluded?
Go ahead.
Chlorofluorocarbons?
Chlorofluorocarbons, CFCs.
Oh, I knew that.
I'm sorry if you said it in here.
I didn't know.
Now, if you get something even hotter, it'll produce X-rays. And so if you go to the doctor and get X-rayed, you're laying under a machine that has an incredibly hot filament inside it. It actually is so hot, it'll produce X-rays. And it takes a lot of power to run that thing to get that little filament hot enough. And all they do when you lay down under the X-ray machine, let's say they're X-raying your arm because you broke it, got in a bar fight or something, I don't know, whatever y'all do. And what they do is they have this machine and it's made of lead. So none of the X-rays will get out the sides because lead will stop X-rays. And then there's a little lead slit, and when they push that button, they open it real quick. It's like a shutter on a camera. It goes, and some of that X-ray radiation comes out from the hot filament. And it'll go right through your arm. But the bones will block a lot of the X-rays, but the soft tissues will let it through. So it basically goes right through the soft tissues and is blocked only by the bone, and they put a little photographic plate underneath it, and the X-rays change the color of the plate if they hit it to white, and then they take a negative of it, and they have a picture of your bones. Isn't that cool? X-rays.
So what happened if you left the X-ray on you for like a while? Like,
It would really damage you bad. And they don't want, you notice the guy leaves the room before he takes the X-ray picture. Have you ever noticed that? He goes behind a wall that's made of lead also.
Didn't they have problems with shoe stores using this all the time?
They did.
And like everyone got cancer.
Oh, I didn't know about that. Yeah, X-rays are very damaging. They'll cause cancer, just like ultraviolet will. But X-rays have a lot more energy, so they'll cause cancer way faster than ultraviolet.
Is that filament always on then?
No, that'd be a very big waste of power.
And how do they get it that hot in that short span of time?
Oh, you can get things hot really good. Yeah, they just apply a lot of energy. It's not a very big filament, but yeah, they don't leave it on. Finally, gamma rays.
Oh boy.
Gamma rays are so high energy that it's almost impossible to produce them in normal circumstances. You can produce them in a nuclear bomb, though. So that big old nuclear bomb back there, as soon as that thing went off, that's a hydrogen bomb, a fusion bomb. As soon as that thing went off, you want to get a shot of it for the viewers at home? They're going, what are they looking at? As soon as that bomb went off, gamma rays were released and shot from it in every direction. And the gamma rays are absorbed by our atmosphere, so they won't travel very far through the atmosphere, just a couple of miles. But anything within those couple of miles is immediately fried by the radiation. I mean, if it hits you, you would be dead in just a number of days. Your cells could break down, and you have all types of problems. The people that were inventing that bomb, a few of them, in messing with the stuff, got radiated from it. And so it's tough stuff. Now, the center of the sun has fusion going on all the time. So the center of the sun creates huge amounts of gamma rays. Huge amounts. But the gamma rays don't escape the center of the sun. They go through the sun's atmosphere, and actually the outside of the sun is not so hot that it's producing any gamma rays. Only the inside of the sun where the fusion is happening. So the sun is a big ball of gas where the inside's really, really hot and producing a lot of gamma rays. But it cools down. The sun actually, you don't use the word cool a lot with the sun, but the sun gets cooler than the center as you go outside. So the outside of the sun, the gases absorb all those gamma rays. The gamma rays never make it to the outside. The outside of the sun is only 8,000 degrees Kelvin, which is real hot. It's hot enough to glow. It's hot enough to produce some X-rays, a lot of ultraviolet, and a lot of the rest of this stuff. But it doesn't produce any gamma rays on the outside of the sun. So we don't have to worry about gamma rays coming from our sun. It's only on the inside.
What else produces a gamma ray besides the...
Nuclear bombs. A nuclear bomb is like a reaction that's going on inside the sun. Man-made. We make that ability. And there's nothing else that really gets that hot on this planet. Now, out in space, you have lots of explosions called supernovas. Have you ever heard that? Some stars, when they die, they'll blow up in a huge explosion that releases more energy than our sun does in the entire 10 billion years of our sun's lifetime. A supernova will release more energy than that in 1 second. And it's so hot, it blasts gamma rays in all directions. And we can sense that from Earth. We can see little gamma ray bursts, they're called, going off in space. You can see it with if you have a gamma ray detector. And again, gamma rays don't go through our atmosphere very well, but you put it out in space on a satellite, it'll detect these little gamma ray bursts. They're explosions that are happening in galaxies all over. And you just see them, they flash like lightning bugs. But you need those detectors to see them. And this is why space, here on Earth we're protected by our atmosphere, but if you're out in space, that's a dangerous place. Now these gamma rays that are coming from far away can hit you. And even though there's not much of them, because they're coming from so far away, all these little explosions, it can eventually hurt you. So you have to wear protective gear, and they have to worry about that with our astronauts.
So do they wear lead suits?
No, but they limit your exposure they don't want you out there for very long on walking on the moon, spacewalks, and things like that. You're only supposed to go for a certain number of hours, and then they say that's enough. Any more, and you'll get too much damage. One of the things they're trying to plan is a mission to Mars, where they fly people to Mars and they land them there, and they have the astronauts work on Mars for a while. And the thing is, to make that work, because Mars is so far away, and the Earth is in orbit like this around the Sun, and Mars is in a slower orbit. The Earth only comes close to Mars about every year and a half or so. And no, I'm sorry, that's not right. About every year, I guess it would be. Well, but Mars is moving too. Maybe it is a year and a half. About a year and a half. And that's when you have to launch to Mars, and then you have to wait on Mars until the Earth comes back around, and then you fly back. You see? And so there's a gap there of time where you're going to have to stand on Mars if you're an astronaut and wait there for the Earth to come back around, and that time is they're scared they'll get too much radiation, so they'll have to have something to protect them.
I thought there was an atmosphere on Mars.
It's a very thin atmosphere of carbon dioxide that doesn't protect you from the radiation. So what they'll probably have to do is get to Mars and either build a habitat or land in a habitat that has some protection from radiation.
That's cheating.
Which makes it heavier, but maybe they could use Martian rocks and build like an igloo or something. That's what they're talking about doing. Because it's heavy to carry all this stuff from Earth. Why not just use what's there? And the rocks will protect you. So you might see in the future people on Mars in little rock igloos.
I thought our space program was over now.
Just we don't have as much money to spend on it as we'd like, but it's still going. Still going well. Okay, so have you ever heard of a black body spectrum? Probably not. A black body is a fictional thing that's black colored. Imagine a black spherical ball, like a baseball, except it's totally black. We would say that's a black body. In a fictional black body, what it does is it absorbs all the radiation that hits it. There's nothing that absorbs all the radiation that hits it. But let's imagine that there is. They call it a black body. And as it absorbs the radiation, it heats up, and then it re-emits the radiation. And it re-emits the radiation in a certain curve that we call a black body curve. I don't know why. I don't need to draw it up here. I have it here. This is what a black body curve looks like. And what happens is the hotter the object, the larger this curve gets. I probably do need to draw this.
Maybe we're back to the other side while you draw.
There you go. I'm missing an eraser. Here it is. Okay, so here we have a graph with energy on the side and frequency on the bottom, where low frequency is over here and high frequency is over here. Now, a cold object will have a black body curve that looks like this. That means it's not releasing much radiation. And it's releasing it at low frequency. What do we call low frequency radiation? What's the word for that?
Radio.
Radio waves. But the hotter an object gets, the larger this black body curve gets. That's a hotter object. Here's an even hotter object. Here's an even hotter object. So the curve just keeps growing as the object gets hotter. This is the radiation that is released from a hot object. And you can see it's not even. Radiation, the shape of that curve, can I turn now? Turning anyway. the shape of this curve, the radiation falls off at high frequencies. And there's always a peak. So at a certain temperature object releases most of its energy at a certain frequency. We call this a black body curve. And there are some basic rules called the radiation laws that come from this, which is on page 52 is where it talks about this. Make sure I don't run out of time here. Yes. As the temperature of an object increases, the curve shifts toward higher frequencies and intensities, while the shape of the curve stays the same. So, cold object, warmer, hotter, even hotter. And so, if we think about the electromagnetic spectrum, radio is over here, gamma is over here. And so, to release gamma rays, you have to have a really hot object. Hot object. In this one, right here, this is a cold object. Is your body releasing any electromagnetic waves right now?
Yeah.
What do you think it's releasing?
Infrared. Never mind.
It's not hot. Your body's not hot enough to release gamma rays. Is it hot enough to release visible light?
No.
If it was, you'd be glowing,
There's proteins.
and you're not. Is it hot enough to release infrared?
Yes. Well,
How do you know?
because you can feel your forehead and stuff.
Yeah, you're warm, aren't you? You feel somebody's arm, they're warm. You can feel the warmth. That's infrared. Isn't that interesting? Wien's law, the hotter the object, the higher frequency or bluer the radiation. Stephan's law, the hotter the object, the more total radiation is emitted. So the area under the curve is the total radiation. So a very hot object releases a lot of radiation, a cold object just a little radiation. These are the radiation laws. You will impress your physics teacher if you know the radiation laws. I have to turn from this. I know you might not be done typing, but I have to turn. So here's a cold body in space. This picture. Look on page 53. Now, they drew these lines in, so just erase the lines. There's a black cloud there in space. It looks like an area just where there's no stars, but that's not it. What it is a black cloud of material. It's a very cold black cloud, and it produces radiation towards this curve. It's not hot enough to glow, so we don't see any colors. It's not colored, it's just black. But it is releasing some radio waves, and that's what the R means here. The R means radio waves. We can detect that because we took this picture with a radio telescope. A radio telescope is a big dish that can receive radiation. And so this radio telescope is receiving lots of radiation, lots of radio waves from these stars, and some radio waves from that object.
What is that object?
It's called a dark dust cloud. There are dark dust clouds floating out there in space that are cold. 60 Kelvin, that's real cold. Now here's this red glowing gas. This is taken with an infrared telescope so you can see it. It is 600 Kelvin. So it is releasing heat and radio waves and a little bit of light. It's glowing slightly red. See how it would be red colored because a little bit of the radiation released as light. And the black body curve is a lot bigger. That's our sun. And our sun is at 6,000 Kelvin on the surface. And you can see this big hump. I said 8,000 earlier. I guess it's 6,000. I misspoke. Anyway, you can see it peaks here right about in the orange or yellow. Red, orange, and yellow. So our sun appears yellowish. But to our eyes, that aren't as particular about picking out waves as this telescope is, to our eyes it just appears white because we're getting all colors coming at about even levels. But if you have a sensitive telescope that can distinguish between colors very well, our sun is yellow. It's yellow-orange because that's where the peak of the radiation is coming out. And here is a cluster of stars. It's called a star cluster. And it's so freaking hot in there because there's a whole bunch of stars real close together that it goes all the way over. And it's releasing light, so you can see it. It looks kind of bluish. There's more blue than there is red, so it looks a little bluish white. But it's also releasing a heck of a lot of ultraviolet. So you read 2.3 and 2.4.